Good evening. This is going to be the first presentation for our second unit, Reactions in Aqueous Solution. The following learning objectives will be covered in this video. The student can draw and/or interpret representations of solutions that show the interactions between the solute and the solvent. The student is able to create or interpret representations that link the concept of molarity with particle view of solutions. The student is able to apply Coulomb's law qualitatively, including using representations to describe the interactions of ions and the attractions between ions and solvents to explain the factors that contribute to the solubility of ionic compounds. Students can translate among macroscopic observations of change, chemical equations, and particle views. The student can translate an observed chemical change into a balanced chemical equation and justify the choice of equation type, molecular, ionic, or net ionic in terms of utility for the given circumstances. To begin our conversation on solutions, we need to define a solution as a homogeneous mixture of two or more pure substances. The solvent is present in greatest amount. All other substances are solutes. Water is often referred to as the universal solvent. It has many properties that are unique to a compound of its size and type, meaning that it is a small covalent compound. These types of properties you would see with a high specific heat, meaning that it would require a lot of energy to raise the temperature of 1 gram of the substance by 1 degree Celsius. It will have a high heat of vaporization, which means that it will also require a lot of energy in order to convert 1 mole of the liquid into a gaseous molecules. And it also has very strong cohesive and adhesive forces, which are talking about the binding of molecules that are like in type, i.e. other water molecules, and also for adhesive qualities, molecules of different types. One of the most important substances on the earth is water. Life could not exist without it. It has the ability to dissolve many different substances, and that is due to its polar nature for the molecule. It is a polar molecule because it has an unequal charge distribution. You can see with the molecule to the right here, it would also have in this ball and stick model, it would have 2 sets of lone pair electrons on it as well, but you can tell it's a polar molecule based on the partial charges that you see listed out here with the partial positive and negatives. The symbol that you see here is the lowercase delta sign. And we have 2 positively charged areas of the molecule, and we have one negatively charged area around the oxygen. We have the center of positive and negative charge not being in the same place, so it would create a permanent dipole within the molecule. One thing to note here as you see this molecule is due to the fact that we have these 2 sets of lone pair electrons, they are going to cause the molecule's bond angle to be slightly less than what we would anticipate for something that has 4 electron domains. Due to the fact that they do not have a bond with another atom, they're not held quite as tightly, and so they're able to spread out just a little bit more. And by spreading out a little bit more, it's going to force the OH bonds to come in slightly to where it is now 105 degrees instead of the expected 109.5. Now, the last thing that we're going to mention here is just a concept. When something does dissolve and water is the solvent, we have a process that we call hydration. We have the oppositely charged particles. So we have the opposite charge ions attracting to the polar ends of the water molecule. And so when we look at whether or not a compound will actually dissolve, we look at the forces of attraction that are taking place. If we have a attraction that's stronger for the water with the ions of the crystal lattice that is trying to be dissolved, then the dissolving process will take place. If the force of attraction is stronger between the ions than it is for the ion and the water, then we would have a precipitate form, and you would have very little amount of that substance that will dissolve. When ionic compounds dissolve in water, they dissociate into ions. Ions become surrounded by water molecules. This is the hydrated concept. When solute particles are surrounded by the solvent molecules, we say that they are solvated. When we look at an example, so if I have something like sodium chloride, NaCl, a very soluble compound in water, take the Na plus ion, it will orient itself with the water molecules so that the oxygen side, again that partial negative side of the water molecule, is coming in close proximity to the sodium ion. So we would have multiple water molecules that would orient themselves in this process and attract themselves to the sodium ion enough so that they are able to separate the sodium ions from the chlorine ions. Please remember that your ionic compounds are found in a crystal lattice where we have a large number of ions that are alternating between positive and negative charges throughout the lattice structure. So when the ionic compound is dissolved in water, the solvent molecules will pull individual ions from the crystal surface and solvate them. This process is called dissociation. So again, it will take it off layer by layer, just kind of cleave all those ions off, layer by layer, whatever's on the outside edge, until that crystal is completely gone. Okay, so let's look at a couple of example problems here for how we would write the dissociation equations. For our first example, we have sodium phosphate, Na3PO4. So for these compounds, we're always talking about them being in the solid state initially, and then they are dissolved in water, because water technically is not part of this reaction, it's just the solvent medium. We're going to write it over the arrow, and now we look at our compound. I have 3 sodium ions and 1 phosphate ion. So I would have a coefficient of 3 for the Na pluses. They now become aqueous. And then I have 1 PO4 3-. We do not separate this into individual phosphorus and oxygen atoms because this is a polyatomic ion, and it would be aqueous as well. As we look at our second example, we have calcium chloride, CaCl2. I would place water up above the arrow, and I would form Ca2 plus and 2 Cl- ions. When an ionic compound dissolves in water, we will form an electrolyte. An electrolyte is a substance that dissociates into ions when it dissolves in water, and it has the ability to conduct an electrical current. We can classify electrolytes as one of 3 types. A strong electrolyte is a substance that completely dissociates into ions when it's dissolved in water. Common examples would include strong acids and bases, and all ionic compounds. A weak electrolyte is a substance that does not completely dissociate but will partially dissociate. Typically around 1% dissociation will take place. Your examples for this would be your weak acids and bases. And then a non-electrolyte may dissolve in water, but it does not dissociate into ions when it does so. So this could be other covalent compounds, such as sugars or alcohol. They are both able to dissolve in water due to the oxygen that's present within the molecules, but they are not able to separate into ions. This is just a little summary table showing all the different types of electrolytes. Wanted to clarify just a couple of things here. As we look at your strong acids, again, we have 6 defined strong acids in AP Chemistry. We have HCl, HBr, HI, HNO3, HClO4, and H2SO4. There are, in some textbooks, a 7th one that would be added in, but these are the 6 that are recognized by College Board. Your strong bases, so again, these are your acids. Your strong bases will be either your group 1 or heavier group 2 metal hydroxides or oxides. One of the things we'll talk about a little bit later is for those non-metal, or those metal oxides, when they have water added to them, they will react and form a hydroxide compound. So if you have a group 1 metal oxide or a heavier group 2, and by that we mean calcium, strontium, barium, if you have those different metals combined with either oxygen or the hydroxide ion, it will be a strong base. One of the ways that we can test for a solution to be an electrolyte or not is by conducting a current with it. So in this conductivity test, you can see with the pure water on the left-hand side, there is no lighting of the light bulb in this apparatus, so you know that that is going to be a non-electrolyte. When you have the sucrose solution, again, there is not the lighting of the wire inside, and so we would classify this one as a non-electrolyte. In the example on the right, you can see as the sodium chloride is dissolved in the solution, you now have the light bulb lighting up when the conductivity tester is placed inside. We have one other possibility, which is not pictured here because it would be very difficult to see, but if you had a weak electrolyte such as vinegar, which is acetic acid, not one of the 6 that we had discussed, what you would see is just a very faint flicker, little redness to the wire, but it would not be enough to illuminate the light bulb. We will now turn our attention to precipitation reactions. A precipitation reaction is one in which 2 aqueous solutions are mixed together and we have the formation of an insoluble compound, a precipitate, that will be created. This can be predicted easily by using your solubility guidelines, something that you need to memorize as we get ready for the AP exam. The process that we use to separate a precipitation reaction is a process called gravimetric analysis. So when you filter the solid that would form, that is what we call gravimetric analysis. We discussed this in our lab last week. So you would again filter out using the vacuum filtration. You would use the suction of the water to pull the solvent through the Buchner funnel, and you would collect the precipitate on the filter paper. It is vital that we know exactly what species are present in a reaction mixture, and by species we mean what types of substances. Are they solids, liquids, gases, or aqueous solutions? If we're able to understand the reactivity, we must be aware of just what is changing during the course of a reaction. The molecular equation lists the reactants and products in their molecular forms. As you can see in the example below, we have silver nitrate in an aqueous solution reacting with a second aqueous solution of potassium chloride. Both of these compounds are completely soluble. The silver, again, because it has the nitrate ion, completely soluble, and then the chloride, because it is bonded to the potassium, group 1 metal, it is also completely soluble. Please refer to your solubility rules to help with this information. On our product side, we have silver chloride and we have potassium nitrate. Again, knowing that we have potassium and nitrate, both completely soluble in anything, they will be aqueous. And then the silver chloride, again, your chlorides are insoluble when they are combined with silver, mercury, lead, and the copper 1 ion. So we know that that will be our precipitate. Inside of the container, what we would find is a white, yellowish colored precipitate for our solid. We can break down the reaction to get a more specific reaction when we look at the ionic equation, or the total ionic equation for the reaction. In this total ionic equation, all your strong electrolytes, strong acids, strong bases, and soluble ionic compounds are dissociated into their ions. You will notice, however, down here at the bottom that the silver chloride is not split into its ions, and that is because of the fact that it is insoluble. Only a very small percentage of those ions will actually dissociate for the silver chloride. However, they are still classified as a strong electrolyte, and that is due to the fact that the small percentage that does actually dissolve will completely dissociate. So this is going to give us a better representation of what's taking place within the solution and the reaction mixture when we look at the total ionic equation. So for this, I would split the silver nitrate into Ag plus and NO3 minus ions, both of which are aqueous, and then potassium and chloride ions that are both aqueous for our second substance. When they mix together, we have the silver chloride that forms as a solid, so again that would be our precipitate, and then we have the potassium and the nitrate ions as well. The net ionic equation is the most accurate representation for a reaction. To form the net ionic equation, cross out anything that does not change from the left side of the equation to the right side. The only things left in the equation are the things that will change or react during the course of the reaction. In this case, the substances that will form the solid, but it could also be a gas or water that would be produced in a neutralization reaction. Those things that do not change or deleted from the net ionic equation are what we call spectator ions. In this example, you can see how I have both nitrate and potassium ions found on each side of the reaction, and there have been no changes in their composition. So I have aqueous nitrate ions, those will cancel. The aqueous potassium on each side will also cancel, and now I'm left just with the silver ion plus the chloride ion forms the solid AgCl. So when you are writing your net ionic equations, the first thing that you want to do is write a balanced molecular equation. You want to then dissociate all of your strong electrolytes, and you will cross out anything that remains unchanged from the left side to the right side of the equation. You would then write the net ionic equation with the species that remain. One big thing I just want to alert you to is that for the number 2, if your compound is a weak electrolyte, so all weak electrolytes and non-electrolytes will be written in their molecular form. So what I mean by that is we're not going to split them up. So because of the fact that those weak electrolytes typically only have about 1% that will dissociate, that means that 99% of them will stay in their molecular form, and so we will treat them as such. So let's now look at an example problem. We have write the net ionic equation for the reaction between nitrous acid and sodium hydroxide. So our first step in that process was to write a balanced molecular equation. So for nitrous acid, that would be HNO2. Be careful, it is aqueous, but this one is a weak acid. Don't get confused with the nitric acid, which is your strong acid. And then I have it reacting with sodium hydroxide, which is a strong base, and it will produce sodium nitrite and water. Double replacement reaction, neutralization reaction. And so there is my step 1 in that process. Now, with this, because this substance is a weak electrolyte, when we're talking about our second part of the equation, anytime that I have a strong electrolyte and I see that aqueous sign, I'm going to split it apart. So in this case, because it's now a weak electrolyte, I'm going to leave it as the HNO2. It's still aqueous, and then I can react that with the Na plus and the OH minus ions, both of which would be aqueous. On my product side, sodium nitrate, or nitrite, excuse me, that is an aqueous solution, so it would also split apart to form sodium ions and nitrite ions. And then I have the water that would be created, and that would be in the liquid state. So I would keep that together. So now, as I look at my total ionic equation, you'll notice that I have only one spectator ion. I have the sodium ion here. Put the aqueous signs on. You don't need to put the state of matter on this for the AP exam, but it's a good habit to get into. So these would be my two spectator ions that I would then cancel, and then everything else would represent my final answer. So I'd have the HNO2 aqueous, I would have the OH minus, and it would form the NO2 minus and the H2O. Again, liquid, aqueous, and aqueous. So that would be my final answer for the net ionic equation. So let's look at one more example, and in this case we're going to look at an example that's occurring between hydrobromic acid and potassium carbonate. Now for this reaction, hydrobromic acid is HBr, potassium carbonate, I have K2CO3, which is aqueous, and now for the products I'm going to get potassium bromide, and we would think it would be carbonic acid, H2CO3. However, this is a special characteristic reaction where the carbonic acid will immediately break down into water and carbon dioxide gas. So for the balancing, I would have 2 for the HBr and 2 for the KBr. When I look at my first step, again, this is a strong acid, so it's going to be a strong electrolyte, and this is a completely soluble ionic compound, so both of them will dissociate. So when I'm doing my total ionic equation, I would have 2H plus aqueous plus 2Br minus plus 2K plus aqueous plus CO3 2 minus aqueous, and that's going to form 2K plus 2Br minus plus H2O as a liquid and CO2 as a gas. So when I look for my spectator ions, hopefully you can see I have 2 Br minuses and I have 2 K pluses. So those will be my spectator ions. And what I have left for my net ionic equation is 2H plus aqueous plus the CO3 2 minus aqueous for the carbonate ion, and that will form water as a liquid and CO2 as a gas. Okay, so this will be our final example for this evening. We're going to write the net ionic equation for the reaction between lithium phosphate and magnesium chloride. So for this reaction, we have lithium phosphate, Li3PO4, that will be aqueous, and magnesium chloride, MgCl2, also aqueous. The products that will form, we'll have lithium chloride and magnesium phosphate, Mg3PO4 parentheses 2, and that will be our solid. Now, again, you would know this by using your solubility rules. When we balance our equation, Notice I have 2 phosphates on the reactant or the product side. I have 1 on the reactant side, so I need a 2 for this coefficient. I have 3 magnesiums versus 1, so I would need 3 for the magnesium chloride, and then I would need 6 for the lithium chlorides to balance it out. So that would be our step 1, getting our balanced molecular equation. When I look at step 2, I have 2 aqueous solutions that are ionic compounds to begin with, so I know both of them will be strong electrolytes. So now from our balanced equation, I'd have 6 Li pluses plus 2 PO4 3 minuses. I would have 3 magnesium 2 plus ions, and I would have 6 chloride ions. On the product side, I'd have 6 Li plus ions and 6 Cl minus ions. And then I would have 1 of the Mg3 PO4 parentheses 2 as a solid. So identifying my spectator ions, I have 6 lithium ions and I have 6 chloride ions found on each side of the reaction. So those would cancel, leaving me with the 2 PO4 3 minuses and the 3 Mg2 pluses. So that would be my net ionic equation, 2 PO4 3 minus plus 3 Mg2 plus. Again, the order does not matter, and we would form Mg3 PO4 parentheses 2 as a solid. So if you guys would please, you can stop the video and go find the practice worksheet on net ionic equations and work through that. Thank you.